Swayam Prabha. Digital India. Educated India.
Example analysis and design verification on a single-story multi-bay moment frame. And I want to use the direct analysis method with this. So here's the frame, and so it's what in the metal building industry we often refer to as a modular frame. It's a very wide frame, and so it would be very expensive to expand the entire interior here with a clear span portal frame. If we can drop small columns down to take gravity load out of the roof, then that's going to be much more economical. So plenty of building footprint out there that has frames that look like this. In terms of the lateral load resisting system, it's the exterior columns, the little triangles there mean it's a rigid connection of the roof girders to the columns there on the end. And so the members sizes that you see here, yield strength of the steel is 345 megapascals. We've got these dead snow and wind loads, and we're going to focus mostly on load combination 1. There's a few slides that illustrate load combination 2 as well. But we'll focus just on load combination 1 here, and you can, the load combination 2 slides are just for your further edification if you would like. So our columns here are braced out of plane, but just at the top and the bottom. The girders are braced at basically 5 foot or 1.524 meter center to center by purlins and flange diagonals to the bottom flange of the roof girder wherever needed. So that's the system. Now, a few other things. Often when I do this example with my class at Georgia Tech, I'll bring some handouts on some of these pages so you can kind of keep these in front of you as we're looking at some further things. So these is kind of a summary of information that we'll use as we're moving further in terms of the section properties and some of the capacity properties for these members. So big picture here. This is the type of structure if you're thinking about where can I encounter the largest second order effects where I have to be really careful. It's not on a high rise. On a high rise, lateral load is important, but we're going to need to control stiffness on a tall frame. And you're going to you get P delta effects, not like what we're seeing here. In a structure like this, it's very little wall area there on the end of the building to catch wind. You're not getting big wind loads on the overall structure, relatively speaking. The structure tends to be relatively light, so seismic is relatively small. But if you're in an area where you got a big snow event, you got a huge amount of load on that from snow on that roof, and it's a big footprint of the building. Guess what? Because your wind loads were low, your seismic loads were low, you don't have much lateral stiffness, but now you got a huge vertical load, you're going to have a tremendous second order effect. So, and metal buildings, typically the metal siding is the cladding on the structure is very forgiving, very flexible often, and so we can tolerate large drifts. We don't have to worry about controlling drift for serviceability considerations. Okay, everything's in the mix there to where you got to be really careful on this sort of a structure with your sidesway stability effects. So again, if you want to kind of keep this page in mind, Again, this is something where often I'll provide this as also as a handout so you can look back at this while we're working through things. There's nothing special about what I'm showing you here on this page. It's a way that I'm going to set things up to do the bookkeeping for our analysis. What I want to do is, let me just do a unit lateral load analysis on the structure and document what moments and axial forces am I going to get. And then for whatever values of axial forces, lateral load I need to work with later, I can multiply that by what the results for the unit lateral load and add the effects up. Okay? So there's my unit lateral loads. I'm putting half on each side of the building just to avoid any small axial shortening or axial elongation effects in the roof girders. If we consider the first order side sway due to H, and so this, I need to make sure that we're all on the same page with, we're running direct analysis method here. And so by AISC rules, since this is we're looking at load combination 1. For load combination 1, it's a gravity load combination, so I need to put in and out of plumbness. I'm required. Or an equivalent notional lateral load. 0.002 Y sub I for us, again, I see the Indian standard would use 0.005. But here's where things are very different in the Americas. We would say, on this frame, if I'm going to do direct analysis method, I'm going to analyze everything with 0.8 of the nominal elastic stiffness. That's a very rough attempt to approximate. I'm going to lose some stiffness from yielding, etc., as we're approaching strength conditions. Okay? So all these analyses are being done that way. Well, these are first order analyses. So this is if I do the analysis and I find, well, what's my first order drift? It's 1.698 millimeters. That's with the reduced stiffness. And so I can do a PL story here on this, H divided by delta H over L. And so I get from that calculation 3,590 kilonewtons per radian. And that's a stiffness in terms of a drift ratio. If I want to think about, well, what are the two columns on the ends of the building doing? They're both essentially contributing half of that story lateral stiffness. So PL being just the stiffness, lateral stiffness for an individual column, half of PL story here. And if I equate that to, and so this is just a way of trying to understand what sort of stiffness characteristics do we have in our structure here. So I could calculate a PL as a coefficient times my 0.80 I divided by L squared. So if I take that, I know E, I know I of the column, I don't know beta L, I know L, I equate that to half of PL story, solve for beta L, I get 1.884. Now let me ask you, check to see how well you're following at this point in the day. If the roof girders were very massive and very stiff compared to the columns, what should beta L be? What number? Difficult question. Yeah, it's just a number. So I'll give you a very generous hint. Before we had a cantilever, and the sidesway stiffness was 3 I over L squared. If the girders here are essentially rigid, what do you think? 3? If I have a rigid girder, I'm looking at the sidesway stiffness of that column, it's essentially an inverted cantilever, right? And so I'm saying that so we can kind of get a feel for what are the stiffness characteristics of the system like. You've got 1.884, so that's because of the flexibility of the roof girders. If the roof girders were rigid, I'd get to 3. All right, I'm going to do also a unit gravity load for bookkeeping purposes. So we'll need to kind of glance back here with some of the things we're going to do in a minute for the bookkeeping. All right, so let's analyze load combination 1. It's 1.2 dead plus 1.6 snow. We want to look at checking our design by the direct analysis method. We'll use the amplified story drift method and the B1, B2, or NTLT method that I showed you earlier, and we'll compare to general purpose analysis results. All right, so we need, if we're going to use an amplified first order analysis, we need B2. Our distributed load, our factored vertical load on the roof girders is 45.5 kilonewtons per meter. And so if you do QU times 5 bays, each bay is 12.19 meters, we've got a whopping 2,773 kilonewtons vertical load that's being stabilized by the lateral load resisting system, we hope. All right, and so you can say, well, what's the leeward column axial force? So if you go back to the unit vertical load slide that I showed you a minute ago, the leeward columns given a unit vertical load had an axial force of 5.304 kilonewtons. So multiply that, or 5.304 kilonewtons per unit kilonewton meters on the roof. So if I multiply that by QU, so just from gravity load, my leeward columns have 241 kilonewtons in them. Those are the only moment frame columns here. The 2 exterior columns are moment frame columns. Everything else is a gravity column. It's leaning, right? And so my PMF is 2 times PU, 482. I need an R sub M. I can get that since I've got P story and PMF. Okay, R sub M is getting very close to 1 on a frame like this. That's not uncommon when we have a lot of gravity framing, 0.974. Now the direct analysis method, if we have heavy axial load in the columns larger than 50% of the yield load, the direct analysis requires that we also apply an additional inelastic stiffness reduction factor to the columns, but P over PY is only 0.057, so that stiffness reduction factor is 1. All right? Now, I didn't really show you this notation before, but Appendix 8 basically refers to it as PE story, and that PE story is the estimate of the story elastic buckling load, and it's equal to R sub M times PL story. Okay, we did look at that before. And so if we do R sub M times PL story, 3497. But very close to PL story. So notice, again, this whole emphasis of stiffness with our analysis relative to the vertical load that we're stabilizing. Those are the 2 big gorillas in the room. Okay? And yeah, why did we call a stiffness a PL? Because ultimately the elastic buckling load of the frame is close to PL. We're just hitting it with R sub M to account for some P small delta effects on the large delta. All right, so we're ready to calculate our B2 factor. And we get 4.83 with this reduced stiffness. So holy smokes, that is a huge amplifier. Are you serious? Okay. If you do the analysis of this frame without, basically with nominal stiffness, you get 2.74. And those of you at practice would say, I would never want to design a frame that's working like this. Well, with some of these modular frames, that's the economical design. All right, so this should kind of raise some red flags, but let's continue. This frame is actually going to work. It has a lot of drift. A lot of second order effect, but it works. All right, we're going to do notional lateral load to get our approximations. So again, by the American standard, we use 1 in 500 times the vertical load at each level just being the roof here. So our notional lateral load with the 22773 for the total load, we get 5.546 kilonewtons. And say, well, what sort of lateral deflection do we get in our frame due to the notional load? Well, our lateral deflection due to unit load was 1.698, and so we're looking at 9.717 millimeters lateral movement due to the notional lateral load. This is a first order effect. If you said, okay, the frame is out of plumb, the first order effect of the vertical loads acting through that out of plumbness would give us a 9.717 millimeter lateral deflection. But for design, if we're checking second order drift, we need to hit that with our amplifier B2. And so, okay, this frame is drifting by 45.48 millimeters under this factored gravity loading. Again, remember when we're doing strength factored loads, these are loads that we hope the structure will never see. But we design for those loads because we are required to have sufficient strength. And there are serviceability design considerations, of course, that we generally use in structures, but when it comes to the satisfying strength, generally you could say, well, oh, the structure took the load, I'm happy. It worked. Okay? It may look like sin in terms of huge deflections, all distorted, but it took the load. We're good. Okay, now let me do serviceability and fix a few things. All right, and for these metal buildings, we're able to tolerate a high drift, so it may not be a problem. I'm going to work the amplified story drift method. So in addition to what we just did with the notional load, we need a HP delta shear. So that's why I got the second order drift. So the P delta force that represents the effects of the lateral movement that we get, again, this is actually a symmetrical frame, symmetrically loaded, so without any initial out of plumbness, there's no movement. But the notional load gives us the first order effect of that out of plumbness. Then we consider the additional second order effect. How much more does it move once we put the load on there? And that's what the HP delta is working on here. So the HP delta story shears, those are 20.69 kilonewtons. So I need to take the combination of that plus the notional load. That's my lateral loading effect that's equivalent to what the vertical loads are doing and acting through the lateral drift. All right, so given that, we can now calculate a column force. We get some additive compression on the leeward side because of the overturning effects of basically the P delta. And so those effects are, well, 241 was just from our gravity load that we calculated earlier. We just did our notional load plus the P delta shear. 0.317 is the axial force for a unit lateral load, if we go back to the previous slide. And so my overturning effects and the second order effects are basically increasing my axial compression in the leeward column by about 8 kilonewtons to 249 kilonewtons. Generally, we need to check a non-sway amplifier here. So if we do that, again, this is part of the analysis, so I use a reduced stiffness here as well. So you see the 0.8E here in this equation. And so the PE1 here is 9434. C sub m, anybody tell me what the C sub m should be on the column? 0.6. We've used it multiple times now. It's just the first order moment diagram is linear, so we go with that. C sub m is 0.6. And so we do a B1. Again, you do a few of these and you realize that B1 is 1 for these. Okay. All right, so the way the amplified story drift method works, we've got the moment at the top of the leeward column. Due to a unit vertical load, it would be 4.684, but the vertical load is actually 45.5. And due to a new unit lateral load, it would be 6.096. And we get half distributed to each of the columns here from the notional load plus the P delta shear. And so the combination of all that gives us 293 kilonewton meters. That's our amplified story drift method estimate of the moment we need for the design of this column. And we can do the same thing by the NT-LT method, so same B1, same B2, but we need NT and LT moments and axial forces, and then we do the B1 times the NT value plus B2 times the LT, except for the axial force, it's just a PNT plus B2 PLT. And these are similar, but actually a little less accurate than what I just showed you with the amplified story drift method. And if we compare everything, so if we run a general purpose analysis here with your favorite software, okay, 249. So pretty much right on the nose to 3 significant digits with the amplified story drift method. Just a wee bit conservative with the NT-LT method. The moment, okay, all right, we're between 1 to 2% larger than the rigorous solution. And the B2 in terms of second order drift to first order drift, 4.515. So pretty good results, but you could say, oh, all right, but if we've got a tool like Consteel, Mastan, SAP, whatever software you're using, just run once you've got the structure, you're just going to analyze it. You're not going to go through the trouble typically of doing all these amplifiers and manipulations and all. Other than, again, having B1, B2 values, these are all things that you can use as useful indices to understand how your design is working. All right, so let's do a leeward column resistance check. So I get a little bit into the resistance calculations here. And so with the direct analysis method, we need to basically look at flexural buckling of the column either out of plane or in plane. But out of plane is clearly going to control here with the direct analysis method. The routine practice with direct analysis method is you're allowed to use K factors equal to 1 because you've already accounted for in-plane stability effects through putting in the notional lateral load and by putting in the reduction in stiffness. So I would have an L over Rx, but Rx is going to be much larger than Ry. I've got an L over Ry here since I have bracing only top and bottom out of plane, so that's going to be the governing slenderness for the column. The weak axis flexural buckling governs. And so if we put that into the equation for the flexural buckling stress of the column, basically the Euler formula, we get 310 megapascals. And notice there's no stiffness reduction here. So this is a it's often a confusing matter with direct analysis method. You have to look at it in two separate sets of solutions. You do your analysis with reduced stiffness, but then when you move to calculating resistances, if you see an elastic modulus there, it's the unreduced modulus. We can check our level of axial stress in the column. It's fairly low. FU to FEY is only 0.068. That's less than 0.1. And so there's a rule actually in Design Guide 25 for design of frames of non-prismatic members. If your axial load level is less than 10% of the yield load level in the column, you can just use the cross-section strength, which in this case is yield load. So a phi factor 0.9 on yield load, so 3,825 kilonewtons. And I can, if my column flange or web were classified, if I either were classified as non-slender, I have to do an effective yield load of the column. Here in this case, they're both non-slender. Now, for the flexural resistance, we need a moment gradient modifier, and for a triangular moment diagram, we typically use C sub B as 1.75. That's a modifier to account for the fact the moment is not uniform when we're designing the member for flexure. And there's the plateau strength. Turns out that this W12 by 65 is just slightly non-compact, basically meaning it's slightly into, I believe, if I'm correct with Indy code, it parallels Eurocode, and you say this is class 3. So class 3 flange. Okay, or semi-compact, okay. And so if we did the calculation there, the plateau strength, considering the reduction for the flange local buckling is just 1% or 2%, and it's 483 kilonewton meters. Now, there's equations for the flexural resistance in the Americas that are very different than the Eurocode equations. And there's an L sub R term that is basically where we start to consider, if we're less than LR, we consider inelasticity in the flexural strength. Well, LR is 35.1, and the strength at LR is generally, even for uniform bending, is going to be larger than 1 over 1.75, or C sub B. I'm going to show more of this that maybe make it more clear when we talk about flexure a little bit later. But in the U.S. practice, we have a very convenient and a rule that works pretty well for rolled sections. It works very poorly once you get into some other types of sections, so I'll show you some things about that later. And that's what we just scale the uniform bending moment diagram by this moment gradient modifier, and if we're lucky, in which case here, that's 1.75. So scaling from that, I can see based on basically where I am with the L sub R, I'm going to scale to where I get up on the plateau. So I very quickly can write, oh yeah, my moment strength is going to be the plateau resistance here, VMP prime. So those are our flexural strengths and our axial strengths for the leeward column. We need a demand to capacity ratio for the axial term, so that's 0.065. And so the interaction equation we use in AISC. We were looking at a little bit yesterday. It's a bilinear equation, and so we're in the part kind of below the knee of this bilinear equation, where the axial load term gets divided by 2, and then we add that with the mu over phi mn. So we saw that we had some tremendous second order Sidesway amplification in this frame, but the unity check is 0.63. It passes. Now, if we add just a little more load to this frame, we got even more lateral deflection, more amplification. So it's not like we can apply a large amount of additional load to this frame. So that's what this slide is saying. Some engineers might say, well, does this mean I could apply 59% more load to this frame? We're going to see that no, that's not going to work. It's typically, and this is something that engineers have to be careful with the direct analysis method. And it's an approach, it's a poor person's test simulation. We're not trying to use that in a design context. Well, if you're doing a structural test and you're getting very close to the stability limit, what happens? You add a little bit more load, it starts deflecting a lot, you're starting to get a huge amount of nonlinearity, your moments are taken off. Okay, so that's what we're trying to capture that, but it's not very friendly in terms of actually understanding, well, how much more load can we put on this. There's also some roof girder checks on this, but I usually, in my class, I say, okay, kind of look at that. It's kind of a very dense summary of how you could also check the girders here, and so those are good. I think maybe might be good to, since we're right at 6 o'clock, maybe we'll call a timeout for the day and stay within time, and then we'll pick up and do the last piece here that is the topic where we'll look at how does all this work relative to some test simulation results, where we do a full-blown plastic zone, full nonlinear analysis, and compare our results here to what we're getting. That's probably a good one to see when we're fresh tomorrow. Some important takeaways there in terms of how does direct analysis method work, how does the real frame working here for this very Sidesway stability critical frame versus, well, hey, if we're using effective length method, we can still get the frame, it still will work to a certain extent, but the effective length method has its weaknesses for a structure like this. So this is where my colleagues in Eurocode would say, look, we don't believe in stiffness reduction. We're just going to increase the notional lateral load. And so now you have to figure out how to get a notional lateral load that will work. But that's just Ayrton Perry, essentially. We can figure out how to do that. So we have these differences in philosophies. My understanding of the Indian code doesn't go there with any of those. It's really very, very close to what we'd say is an effective length method in terms of the overall solution. Is that correct? And then the checks with the column resistance, with the beam resistance, are very close to Eurocode. Belint was very excited about that. He wants to show you what Consteel can do with Eurocode type calculations at the end of the course. But we're not going to confuse you by talking about 3 different codes in the course. It's confusing enough to talk about an American code you're not as familiar with, and trying to relate that back to the Indian code. I think that's a good place to stop. Sorry?
I just have one comment.
Yeah, go ahead.
I know that's not what we're doing here, but we talk about this, but when they do the general purpose analysis, they would still run a second order analysis.
That is correct.
I think I don't know if I missed that
Okay.
but
Yes.
I was not sure if
Yeah, that's a good point. Yeah, there's so many subtleties with all this, it's easy to miss one. And so that is correct. So I showed you this all in the context of first order analysis with amplifications, just to illustrate that, hey, this is a fairly critical frame, and that amplified the story drift method or the NTLT analysis gives very good results compared to the general purpose analysis. If you're running the general purpose analysis, you would run it either with a notional load or with an explicit out of plumbness in the structure, and you would run it with a stiffness reduction of 0.8 on all contributions to your elastic stiffnesses. That's a very coarse attempt to account for reductions that actually happen in the physical structure. I think that's good. It's 6:01, so I ran over. So maybe we can, if there's any comments or questions, we can still chat some. Anything on your mind? Sorry, go ahead.
So this particular problem, whatever we seen the example.
Yes.
So what is the first order moment, and we see the direct analysis method utility ratios.
Yes.
So what could be the first order analysis if we do?
That's a good question. I don't really have it directly in front of us here on the slides, but the fact that let's see, it's probably easiest to see it with the NTLT method, I think. Yeah. So if we take the NT and LT forces here, or moments, if we set B2 equal to 1 here, then you'd get the first order result. And our B2 is 4.83. So you can see we're getting some huge larger effects in this structure.
So it means that if we do a frame by first order analysis, and if we go to direct analysis second order, and we can see this is amplified almost 4 times.
Yeah, that is correct.
Okay.
Huge amplification.
So whatever the buildings we are designing with first order analysis, if we do the same with second order, the direct analysis method, it will fail by 4 times.
So this is a first order analysis here, and so we've incorporated that amplification and gotten our results. But that is correct. That actually scared a lot of people in Lemessurier's work when that was first published, and some other things in the United States practice, kind of presentations, and engineers would be at the seminar and say, "What? I haven't designed my frame that way."
Yeah. See, sir, the second order analysis, whatever we are discussing, are new trend.
Correct.
Till now, whatever the 50-60 years we designed the building, which is not unsafe. We seen in the already it is active. It is worked, and it may be 50 years lifespan already crossed.
Right.
So what is the result it gives?
Yeah. I'm showing you a frame that it theoretically does not have much in terms of cladding that would help it out.
Correct.
But in many building structures, there's a lot of help from the cladding, right? And I see in the Indian Code there's some explicit provisions that try to incorporate that.
Correct.
I think largely come from British standard, if I understand.
Correct.
so you could also look at this analysis. So I analyzed this frame. I think it's a typical assumption that metal building designers would often use, and that's, I did not count on any rotational restraint at the base of the frame.
Correct.
And I was kind of very interested in seeing that the Indian standard gave some very specific instructions on, okay, here is what you might use for a rotational stiffness to approximate some help you might be getting from incidental restraint from a foundation, right?
Yes, sir. Sir, as such
Yeah.
Indian
Yes.
conditions, metal
Yes.
buildings, almost more than 60% of the buildings are designed as per American code.
For American code, uh-huh.
Yeah. It is
Okay.
40% which are officially required Indian code design only we follow. Otherwise,
Okay.
we go with American only. So,
Okay.
and these numbers are shocking. I cannot discuss or
Yeah.
explain to any of my colleagues.
Yeah, well, I've shown you, if it can be any solace, I'm showing you basically a worst case problem here, right? But you can definitely have, this is a frame that works.
Yeah.
You would hope that the engineer recognizes, oh, this is a frame that doesn't have much stiffness, has a big footprint, it's going to have a heavy gravity load. Okay, I got to be careful.
Yeah, correct.
And of course, this falls in the category that my understanding of the Indian code would basically say you better run a second order analysis, right? And the Eurocode would say, yeah, you got to do some special considerations here on this frame. It's got a lot going on.
Correct.
The American approach would say, okay, yeah, we've done the stiffness reduction. You can see that it's very sensitive. So the frame with nominal stiffness had an amplification of, I think, about 2.7. But once we reduced the stiffness by 20%, it jumps up to
Correct.
4.8, right? Which is that means it's stability critical. Things are starting to get very sensitive to little things.
Correct.
Yeah. Thanks for the
Thank you,
for
sir.
the points and the question.